Hello and welcome to this course called Introduction to Haskell. The main idea of this course is to learn the basics of the Haskell programming language and functional programming in order to then be able to learn and understand more about Plutus, which is the smart contract language for Cardano and is based on Haskell. The course videos will follow a two-part format, the first part being a presentation like this one, and the second part being a more practical demonstration of what was covered in the presentation part. The course materials are also available as a Git book, so there are written materials available on this URL, haskell.hpmeducation.com, so feel free to check that out as well. And that's it for the introduction, so we'll get started with the first presentation today, which will cover the introduction to Haskell and introduction to functional programming. So what is Haskell? It's a purely functional computer programming language, and here we have some of its characteristics. It's polymorphically typed, statically typed, strongly typed, lazy, and compiled. This is just an introduction to what it is, so I'm not going to explain right now what all of these mean in depth, but throughout the course we will learn about all of these things. For now, probably the most important thing to understand is that Haskell is based on pure functions, or more importantly, just functions. It's based on functions, and let's see what pure functions are in Haskell. So pure functions are basically mathematical functions, and Haskell functions work the same way. Meaning that in mathematics, a function maps input values to the function output. It means that any function given a certain combination of arguments will always produce the same result and will not have any side effects. Nothing else will be changed. The function will just take its inputs and produce the output. And if the input is the same, the output will always be the same. So here we have an example of a mathematical function which takes in the argument x and multiplies it by 3. So we can see that if we use the argument 2 as the argument, the output of the function will always be 6. There is no other possible output if the argument is 2. Same if we put minus 5, the output will always be minus 15. Nothing else. Nothing more, nothing less. Okay, so this is the main point of pure functions, that they do not have any side effects. So in a programming language, we can usually print to the screen, for example. A pure function cannot do anything other than take the input and compute its output. That's it. It cannot print to the screen, it cannot make an HTTP request, it cannot do anything like that. So if we have a programming language that cannot do anything except compute some values from functions, then we have a pretty useless programming language. And that's why side effects in Haskell are still made possible through the monad class, but that will come later in the course. For now, it's important to understand that it is based on pure functions. There are still ways to make side effects happen and to build real-world application. After all, the entire Cardano node and all of the toolchain for Cardano is built on Haskell pretty much. The previous slide showed an example of a mathematical function written in the language of mathematics, and now we will see how to translate that into the Haskell language, or in other words, how to define a function in Haskell. So to define a function in Haskell, we use an equation that specifies 3 things. First of all, the function name, which must be unique. Secondly, the names of its arguments, or one argument or many. And thirdly, the function body. And the function body specifies what the function actually does. The function body comes after the equation sign. So to translate our tripling function from the last slide to Haskell, we would write it like this. We would set a name for the function, in this case triple. We would list its arguments. In this case, there is only one argument, x, and that's the first two parts of the function done. Then it's followed by the equation sign, and then this is the function body. And in this case, we just want to multiply the argument x by 3. So this is the general way of defining functions in Haskell. So how do we apply functions in Haskell? We defined on the previous slide a function triple, and now we can apply it by specifying the function name and its argument. In this case, we have just one argument, and so to apply a function, we just use the function name and then replace the x with an actual argument, in this case 4, and the function will calculate its result, in this case 12, and it does so in a few steps, as we will explore later as well, but just to illustrate it now. So first there is a triple function, so it is a function that is being applied to the argument 4, and then it reads from the function body, which is 3 times x. It replaces the x with the 4, and then the multiplication operator is also a function. So then it applies 3 multiplied by 4 and finally produces the result 12. This is how we apply functions in Haskell, by specifying the function name and using the argument we want to apply it to. So now that we have a very basic understanding of functions in Haskell, let's talk a little bit about functional programming in general as a programming style. And in functional programming, the basic method of computation is the application of functions to arguments. In general, this means that a functional program, once ran, will trigger a sequence of functions being applied to one another to finally get to whatever the program is supposed to do. On the other hand, in imperative programming, that basic method of computation is changing stored values via sequences of instructions. So once a program is ran, an imperative program, it will follow a sequence of instructions on how to do what it's supposed to do, rather than necessarily applying functions from beginning to end to get to its result. So to better understand this, here's an example of a program that is supposed to calculate the sum of natural numbers between 1 and n. And first, on the left side, we have this program written in the C language, which is an imperative language. And we would do it something like initiate the sum value to be 0 at the start, and then have a loop that will loop over all the numbers from 1 to n, and for each number it will increase the sum, so it will change the stored value of sum by the number that's being looped over. On the other hand, in Haskell, in a functional way of writing this program would be just the function sum, which is a predefined function in the prelude library, and the prelude is a standard library for Haskell that contains all the basic functions. And then this is a syntax that we haven't covered yet, but it's a list, like an array of values, and this particular instance creates a list from 1 to the number n. And so the first function of this program is basically create this list of all the numbers between 1 and then apply the function sum to that list, which will sum up all the values in the list. So these are two different implementations of the same thing, one in the imperative language, which follows a sequence of steps that explain how to generate the result, and in Haskell, in the functional language, it's more like telling the program what it needs to calculate rather than giving it explicit steps to how to get the result. Now we'll talk a little bit about Haskell modules, which are just files containing the Haskell source code, and our code can be organized into these modules. So we have some rules which are one file, one module, and the file name should match the module name. So here's an example of module definition for our triple function, or our triple module in this case. We would make a file called triple.hs, .hs being the extension for Haskell code files. And at the start of that file, we would define the module using the module keyword, followed by the module name, in this case triple. So module name triple matches the file name triple.hs. The module name is followed by parentheses, which represent the module interface, and anything inside the parentheses is what is explicitly being exported by the module. We'll say a bit more about the module interface soon, but this is generally followed by where, and after the where keyword we have all our source code, or the module contents. So for our triple module, imagine that we just have our triple function defined here, and now in the interface we say, okay, from this module we are exporting the triple function. We could also omit the module interface completely and just use module triple where and then our source code, in which case everything from the module will be exported by default. But if a module interface is present, and most commonly it is, then only the things that are inside the interface are actually being exported by the module. So imagine that we have another definition here for another function, maybe quadruple, but we don't export it in the interface. Then if we import the triple module and try to use the quadruple function, it won't work because we can only import the triple function from this module, the way this is written. Okay, so that's about it for module declarations, definitions. And here's just a note on comments in Haskell. So comments are parts of the program that are not being evaluated. They are just notes to people who are reading the code. So we have two forms of comments in Haskell. We have the single line comment, which starts with the double dash, and we have multi-line comments which start with open curly braces and a dash, and then once the comment is done over multiple lines, it's closed with the dash and closed curly brackets. GHCI stands for Glasgow Haskell Compiler Interactive. We mentioned at the start that Haskell is a compiled language, which means the source code we write needs to be first compiled down to computer code in order to be executed. This is where GHC, the Glasgow Haskell compiler, comes in, as it's the compiler for the Haskell language. And GHCI is an interpreter, a program that we can run to interactively evaluate Haskell code in the terminal. So we can, for example, write Haskell code in GHCI and we get the result right away without needing to compile it first and then running it, which is quite useful when learning and playing around with Haskell. So GHCI supports a lot of things, and one of them is loading Haskell modules that we talked about in the previous slide. So if we have a module here called practice, and in this case we are omitting the module interface, so everything that we would write here would be automatically exported by the module because there is no interface. And if we want to load our module that we wrote in GHCI, we run the GHCI from the terminal, and we use this load syntax. The colon is generally used to give commands to GHCI. In this case, we use the load command to load our practice module, and it says, okay, one module loaded, and now we can use the triple function from the module. Haskell expressions. We said that applying functions to arguments is our basic mode of computation in functional programming. So we can think of function applications as the building blocks of our programs. In that case, we can also think of expressions as what the building blocks are made of. In other words, anything written in Haskell is an expression. There are many different kinds of expressions, but the two most general types are reducible and irreducible. And a reducible expression, here is an example of one, is an expression that can be further evaluated down to some primitive value, such as here the number 4. 2 plus 2 evaluates down to 4, but 2 plus 2 is an expression in itself and it is reducible. In the irreducible expression example, we have the number 10, which when evaluated just evaluates down to number 10 again. So it's irreducible, it cannot be reduced further. So in the 2 plus 2, we actually have a function being applied. The function is plus, or addition, which adds two numbers together. So 2 plus 2 is an expression, it's a Haskell expression, but it's also a function. So any function in Haskell is at its core an expression. And that's it. We don't have to worry too much about it. It's just know that everything is an expression. We mentioned at the start that Haskell is a lazy language, and that refers to the lazy evaluation of expressions, the way in which expressions are evaluated in Haskell. So lazy evaluation means that expressions are not evaluated until necessary. So until the expression is actually needed by the program, it will not be evaluated. The opposite of this is strict evaluation, in which case every expression is evaluated as soon as it's encountered. So to illustrate this, here's a function, we'll just call it f1. It takes two arguments, x and y, and the function body is just incrementing the first argument x by 1. So the second argument is completely useless, we don't need it. If we apply this function to the arguments 1 and 2 to the power of 58, 2 to the power of 58 being some very large number that certainly needs some time to compute, this second argument, 2 to the power of 58, will never be evaluated because it's not needed. To get the result 2, we just need to take 1 and increment it by 1. So the second argument is never evaluated in this case, and this does save computational time, of course. However, this sort of strategy of lazy evaluation, it can still cause some problems because the expression that is not used is still always stored in memory. It's stored in memory because maybe it will be used later on and it will be evaluated then. But maybe it really never gets evaluated, and in that case we are just storing it in memory for no purpose. But in any case, this can still lead to potential memory issues or memory leakage, where our programs eat up a lot of memory and can cause systems to run out of memory because so many unevaluated expressions are being stored there. Immutability is a very important concept in Haskell and in functional programming, and it means that values of expressions cannot change. Basically, everything in Haskell is immutable, which means once it's assigned, it cannot be changed in memory. This is the opposite of most imperative languages where we can mutate a value of a variable in memory. In Haskell, we cannot do that. So here we have an example of a list of 1, 2, 3 being assigned to A. And then we use the reverse function, reverse being a predefined function to reverse the order of a list. We use the reverse function on A and we get back the result of the reverse list 3, 2, 1. If we check what's the value of A again, we'll again get 1, 2, and 3. So A, once it's set to 1, 2, and 3, it can never change. That's because everything in Haskell is immutable, and the equation sign in Haskell is, unlike other languages or imperative languages, it's not an assignment. It's more like the equation sign as it is in mathematics, meaning A is this, and that's it. So if A is this, it cannot suddenly become something else later on. It's immutable. When it comes to installing Haskell, the recommended way is to use GHCup. You can find it at this URL, haskell.org/ghcup, and this will install the most common toolset for Haskell, which is GHC, the compiler, which comes with the interpreter GHCI as well, and Cabal and Stack are both build and package manager tools for Haskell. We won't concern ourselves with those for a while, but this is the recommended way to install Haskell in any case. So that's it for the first presentation. We covered a bit of an introduction to Haskell and functional programming, and now we're gonna explore some of the things we learned writing actual Haskell code. This first practical session is going to be a short one. We're just going to install the Haskell toolset that we mentioned in the presentation. We're going to explore a little bit the GHCI, the interpreter, and we're going to write some very basic Haskell code to get started. The setup I'll be using for the practical sessions is VS Code. There's a terminal at the bottom, and the code that we write will be here in the top part. The underlying operating system is Linux, Ubuntu, and that's about it. Let's get started. The first thing I want to show you is the HPM Education website for Haskell, and this is the Git book I mentioned at the start of the presentation, where all the materials are available in a Git book form. The session of this video stopped around here at immutability, and the rest of the videos will follow these materials as they are laid out here. And now we want to install the Haskell toolset with GHCup. So for Linux, we can just copy this command, which will download and run a script to install Haskell. So we can just run that, enter, detected the bash shell. So to solve the path, we can append or prepend. Haskell language server, do you want to install? Yes, we want to install. As it says here, it provides some IDE functionality, so it can integrate with different editors and offer you some help when writing Haskell code. Do you want to enable better integration of Stack with GHCup? This means Stack won't install its own GHC versions, but uses GHCups. Yes. We won't really be using Stack, but anyway, if it comes to using versions, let's keep it the same. So there are some system requirements that need to be installed. So we press enter to install those. And now we wait. Looks like it might be done soon. GHC installation successful. Downloading the latest package list from Hackage. Hackage is a central repository for Haskell packages. Okay, done. So it says right here already to start simple REPL. You can run GHCI. To start a new Haskell project in the current directory, run cabal initiate init and interactive way. We're not going to do that now, but we will use cabal later on for starting Haskell projects and managing dependencies and so on. And to install other GHC versions and tools, run GHCup TUI. Now this offers like an interface that in which we can install and uninstall different versions of GHCI. As you can see, there is a lot of them for Cabal and Haskell language server and Stack as well. I'm just showing you this way. We will just use the ones that are checked as recommended and currently in use. So that's the installation done, and we have GHCI available now. Now we have an interpreter for Haskell, and we can already write some Haskell code inside it and see it work. So if we write 2 + 2, this is valid Haskell code, and it evaluates to 4. As we saw in the presentation, we can create lists. So we can create a list this way as 1, 2, 3, and it creates this list. We can also use the function of 2 dots that was shown. So if we create a list this way, it evaluates to the same list. So we saw an example of summing up all the values in a list, and we can do this as well. So you see it's valid Haskell code and it works. And in GHCI we can even define our functions. So if we define our triple function here, we can see it is successfully run, but this is of course just a function definition, so no output. But if we actually apply this function to say number 2, we'll get back 6. Okay, the last thing I want to do in this session is to actually write a Haskell module for this triple function and then load it into GHCI. So I'm gonna leave GHCI now with Control D, and I'm going to create a new file, save it to, not here, but HPM Haskell. Okay, so we'll call the file triple.hs because the module name must match the file name. Okay, now the Haskell language server offers us some help here. So if I click this, it's already going to define the module following the file name, module triple where, and then we can just say triple x is x times 3. Okay, here it offers us a type signature for this function. We're not going to get into that now, but soon enough. But for now, it's not necessary to have it, and this is it. We can forget about the module interface for now, or we can add it. So in parentheses, we put triple, and now triple is explicitly being exported from this module. Okay, this is about it because it's very simple. So if we load up GHCI now, and if we use load, or we can use the shorthand L for load, and we say load triple HS. It compiles the module and it loads it into GHCI, and it works. And now we can have our triple function available in GHCI, loaded from our module. So that's loading modules into GHCI. And the last thing we mentioned in the presentation was immutability. So we can check that here as well. If we set A to be a list of 1, 2, 3, and if we, or for example, set B to be reverse of A, so the reversed list, and if we see what B stands for, it stands for 3, 2, 1, but if we look at A, it's still 1, 2, 3. So once A is assigned, no matter what function we apply to A will never change because it's immutable. The result of a function application will always be something new, which is also immutable. So in this case, B is also immutable. It will always be this 3, 2, 1 because it's the reverse of A. So that's it for this video. Thank you for watching, and I'll see you in the next one. Bye.